Hello everyone, welcome to my talk on less is more, revisiting the Gaussian mechanism for different privacy. My name is Tianxi from Texas Tech. This is joint work with Pan Li. So before I get started, I want to summarize our technical contribution in a nutshell. So we give a geometric representation of the privacy loss in DP and also develop approaches that can be used to design future new DP schemes by leveraging the measure concentration of random geometry objects. So my talk will follow this outline. First, I will talk about background, briefly talk about background on DP and the Gaussian mechanism, and then identify the curse or the limitation on the existing Gaussian mechanism, and then I will show our newly developed scheme called R1 SMG, which refers to a rank 1 singular multivariate Gaussian that can address the limitation in the existing schemes. Then I will point out some open problems. So epsilon delta DP is nowadays the fundamental building block for many of the privacy preserving tasks like database query, data mining, and machine learning or AI. And here is the definition. We say a mechanism M satisfies epsilon delta DP if for any neighboring data set, this condition hold the probability of the privacy loss random variable larger than epsilon is smaller than delta. And the privacy loss random variable is defined as a log of the ratio of the probability. Okay? And the Gaussian mechanism is an essential tool to achieve epsilon DP given a computation of arbitrary dimension. In the literature, there are quite a few variants of the Gaussian mechanism. The first one we refer to the classical Gaussian mechanism developed by De Work et al. Adds IID Gaussian noise to the element of the output fx. And there is an analytic Gaussian mechanism that adds also IID noise to the output, but with different variance. There are also a matrix-variant Gaussian mechanism that adds noise from a matrix-valued Gaussian distribution directly to the fx. All the parameters, like the variance or the covariance matrices of the matrix-valued noise, are all calibrated by the privacy parameter and the sensitivity. Now I will show the limitations of these existing schemes. First, we define a very generic accuracy loss for any mechanism. It is just the differences between the mechanism output and the original query result. Since this is a noise addition, L just equal to the square forbiddance norm of the noise. And when the M is the Gaussian mechanism or is variant, we can show that the expected loss always equal to the trace of the covariance matrix. When M stands for the classical, analytic, or the matrix-variant Gaussian mechanism, the trace can be expressed differently, but they are all lower bounded by the squared sensitivity scaled by some constant, and all those constants have linear dependence on the dimensionality of the query. So we identify the curse that the expected accuracy loss is always on the order of the dimension of your query. And how to lift the curse? Turns out there's already a hint in the book by De Work and Rose. So this slide just restates some of the content in the book. Focusing on the query result, people are interested in the multivariate Gaussian that can obscure an arbitrary difference caused by fx and fx prime. And we know that the multivariate Gaussian is spherical symmetric. That means if you project the noise onto any orthonormal basis, then the coefficient lambda I also attribute to the same univariate Gaussian. Then without loss of generality, you can just assume a V is parallel to one of the bases. Then you can bound the privacy loss just using one-dimensional Gaussian plus the sensitivity. So the hidden clue is the privacy loss in high dimension is only related to one dimension of the Gaussian and the sensitivity. Then that inspires us to develop a new scheme. And recall that we found that multivariate Gaussian whose covariance matrix is rank 1 might already sufficient to achieve epsilon delta dp. So that is our developer scheme. Still, we add noise to fx, but the noise now is represented using v times square root of sigma times z, and v is randomly sampled from a unit sphere embedded in m-dimensional space. So that basically means a random direction shooting from the origin. And then scale it by a univariate Gaussian, and then further scale it by a constant square root of the sigma star. Okay, we require v to be random because that makes the privacy loss random well defined, and it also prevents privacy leakage of utilizing a vector in the null space of the random direction v. Okay, so here is our privacy guarantee on the scheme. As long as the dimension is larger than 2, and the constant sigma star is larger than 2 times the square sensitivity divided by some constant. 1 is the privacy parameter, and 1 is psi, which is represented using a crazy expression where it involves the gamma function. So I will briefly talk about the proof sketch. So in the paper, we show that in high dimension, the privacy loss can be bounded as the sum of the 2 edges of a random triangle. And we all know that for any triangle, the edge is bounded by its diameter of the circle formed around the triangle. And we also know that the diameter equals to any edge divided by the sine value of its opposite angle. And that angle happens to be the angle between 2 random noise applied on 2 different data sets. Then we can bound the privacy loss using value involving the sine value of the random angle. So then we just need to analyze the measure concentration of the angle. And it turns out we can bound the probability of the angle deviated theta 0 from nearly orthogonal. That probability can be shown to be very small, and we set that to be delta, the probability of epsilon dp being filled. And we also show that theta will converge to 2 over pi when dimension approaches to infinity. So that comes to our main conclusion. For any high dimensional query, the expected accuracy loss is decreasing as the dimension increase. When m approaches to infinity, then the accuracy loss is a constant. And that's kind of showing the philosophy of you can hide your data in the crowd when dimension is very high with only limited added noise. Then we also show the property that this scheme is stable. And we use the curtices and skewness to measure the stability of the randomness. So the curtices is a descriptor of the tail extremity. The larger the value of curtices means extremely large random variable cannot be generated. And the skewness describes the bulk of the probability mass. And the larger the skewness means much of the probability mass is concentrated to the left of the PDF, and the right tail is very long. And we prove that among all the Gaussian variants of Gaussian mechanism, we achieve the highest curtices and skewness. But there is one caveat to our scheme. Remember that in classical Gaussian mechanism, we require epsilon smaller than 1, and we have a geometric interpretation. If it is smaller than 1, then the projection of noise can cover the difference between fx and fx prime. If epsilon is too large, then the length of the noise will be too small, so they cannot touch each other. In other words, they cannot obfuscate the difference between the query on neighboring data set. So there is also an upper bound on our scheme, but we are still working on the exactly upper bound. But the rule of thumb is it should be smaller than 1 over dimension times the privacy parameter used in the classical Gaussian mechanism, because we are adding Gaussian noise with only 1 degree of freedom, but they are adding noise with m degree of freedom. And in the paper, we conducted different case studies, but here I will only show the case study on the privacy releasing of the Uber pickups in New York. And remember, we require the privacy budget to be smaller than the 1 over dimension of that used by the classical one. So in this case study, we set the privacy epsilon equals to 10 to the negative 5, and all the others set to 0.5. And we can see we are the most closer to the non-private original Uber pickups and also beat all the other schemes. And we also empirically evaluate the stability, and you can see our empirical PDF plotted in red has much of its mass concentrated to the left, and the right tail is very long. In comparison, all the other curves has a bell shape, and the mass is concentrated in the center. That means in our scheme, it is less likely to generate a noise with large magnitude. And now I will talk about some open problems. The first is, of course, we need to derive the exact privacy regime for our scheme. And the second, we need to study the impact of the degree of freedom in the noise magnitude, its impact on the utility privacy and the stability. And last one is, in our ongoing research, we find that the 1 over the square sign value is attributed to the beta prime distribution. If you plot that, you can see that distribution is highly concentrated around a very small range. So we can leverage the method concentration of beta prime random variable to derive more tight cumulative privacy loss. And in conclusion, we identify the bottlenecks of utility improvement in the existing schemes, and we propose a new DP mechanism that can lift the identified curves. And finally, we leverage the measure concentration of random geometry object to bound the privacy loss so that we can achieve better utility stability. And I'm now happy to take any questions. Thank you.